Hello everyone. This is an intro to Unit 4, Solutions, and their solute concentrations and colligative properties. I didn't draw this, but I think it's a cute way to denote how most scientists record concentrations as moles per liter. And most scientists work with solutions, maybe not computational chemists, but they do model solution dynamics. I myself synthesize molecules and reaction mixtures. I have a friend at Intel that formulates silicon wafer etching solutions, and my med student friends, they deal with IV solutions, so solutions are all over the place. But not all solutions are solids dissolved in liquids. So the first thing I want to talk about are the types of solutions. For instance, air is a solution of gases. Air is what? N2, O2, CO2. What about soda? Soda actually has sugar, which starts out as solid, and carbon dioxide, which starts out as gas. But when you dissolve it in water, we'll denote that over the arrow, you get both of them as aqueous. Sugar aqueous plus carbon dioxide. Aqueous meaning that it's dissolved in water. And the last one I want to discuss is brass. Right, so we have gases in a mixture, we have solids and gases in liquid. Brass is a mixture of two metals. It's an alloy of copper and zinc. All right, what do all of these solutions, well, what do all of these mixtures actually have in common? They are all what's considered homogeneous. Homogeneous or homogeneous, meaning that they are well mixed, the components are evenly distributed, and they cannot be separated by physical means, the components, right? You can't easily remove sugar from soda. You could, with techniques, but with just simple physical means, cannot be separated, like filtration. Filtration, or maybe just literally plucking things out with the tweezers. For instance, you could pick out sand out of water with tweezers, but none of these components can be removed from the solution. Okay, a couple more terminology. Solute. Solute is the lesser component of a mixture. Solvent is the one that's greater. Now, here for soda, we have two solutes, sugar and carbon dioxide, and the solvent would be water. So solute is the lesser component. I teach in Atlanta, and in Atlanta, the tea here is cold and it's full of sugar. So let's have some tea water. Okay. And we're going to put in some sugar. So obviously, and we'll make the sugar pink. So obviously the sugar is the solute, and the tea is the solvent. And we could also talk about concentration. We'll talk more about concentration in a later video, but in simple cases, maybe we have 3 tablespoons. That seems like a lot, actually. 3 tablespoons per, let's say, 400 milliliters. Okay, so what would that be in tablespoons per milliliter? Let me check. Um, maybe we should do it by liter. So 3 divided by 0.4 liters. Oh, so that's, no, let's just say per liter. 7.5 tablespoons per liter. Okay, that's 0.4 liters there. So that's the concentration. Um, but if we use more scientific units, you could think of it as maybe 30 grams per, uh, back to liters, liters. Okay. Now we can saturate the tea with sugar, so that's another term. And when we have a saturated solution, that means that you cannot dissolve under normal conditions. You cannot dissolve more under normal conditions. If you're saturated, cannot dissolve more under normal conditions. What does normal mean? Room temperature, a little bit of shaking perhaps, but room temperature, atmospheric pressure, that you could get a saturated solution. Because if you go past the solubility limit, you get a precipitate. So if you go past the solubility limit, you get a precipitate or solid. Well, you could designate precipitate with solid. You've done this when you did precipitation reactions in General Chemistry 1. So if we saturate the tea with sugar and we add more sugar on top of that, then the extra won't dissolve and you'll get precipitate. But before you get precipitate, you saturate the solution with sugar. I have no idea what my color coding means, so don't try to interpret that. Oh, but there are tricks. Why don't we use blue? There are tricks to get it's called a supersaturated solution. We'll abbreviate solution, SOLN. And this is how kids make rock candy. You get a supersaturated solution of sugar, and then you put a C crystal, and over time, other sugar molecules will start to associate or aggregate rock candy. Okay. Now, I did talk about different types of solutions up here, but we are mostly going to focus on liquid solutions, or solutes. They could be liquid, gas, or solid, dissolved in liquid. So we're looking at liquid solutions. When we talk about new topic, when we talk about dissolving, what do we mean by dissolving? Another way to say dissolving is how well the solvent molecules surround each molecule or ion of solute. So we'll just say each solute particle. And you could almost think of it as a process of solvation. Solvation. Making this kind of solvent cage around a molecule or a particle of solute. How does this happen, or why does this happen? Well, IMF, intermolecular forces, IMF. So those are the attractive forces between different molecules, but in this case we'll call it solvent molecules attracted to solute. Those intermolecular forces play a role. They play the main role in solvation. So when you think about solvation, you could think of, for instance, a sugar molecule. I won't give you the structure, but in tea, yeah, you'll have some attraction between the sugar and hydrogen. You'll have some attraction between the sugar and oxygen. Okay, and those are due via what? Due via IMF or intermolecular forces. Let us review intermolecular forces because that may be a question on an exam. What are the intermolecular forces that help the solvent dissolve the solute? Or what are the IMF attractions that cause solvation of the solute? When we review IMF, why don't we list them in order of strength? And we'll go from weakest to strongest. IMF, and we'll call this axis attractive strength. And it actually goes higher as we go down. Okay, so we're going to start with the, whoops, my bad. We're going to start with the weakest. Okay, the first one is dispersion forces, or some of you know this as London dispersion forces. Okay, those are the weakest. Some people know this as also known as induced dipole because it doesn't use permanent dipoles to have this attraction. Now, London dispersion forces, you might remember, I tried to remember this when I was learning it, they are present in all substances. Every substance can have dispersion forces with another molecule. Present in all molecules, right? When you're listing all the IMFs for a certain molecule, such as, I don't know, such as acetone, then definitely, list London dispersion forces first because all molecules display London dispersion forces. I'll let you review what exactly those are. That's not for this unit. That's was talked about in the past. The next one is dipole-dipole. I'll put it here. Dipole-dipole. And those are present in polar substances. We won't talk about polar and nonpolar molecules here. Probably in the next video or the next couple of videos we'll talk about, not probably, we will talk about polar and nonpolar, but present in polar substances. Polar substances, the definition in general chemistry is the molecule has a net molecular dipole. You're going to want to know geometry, and I promise you we'll go over some examples in the next video showing what is a polar substance and what is a nonpolar substance. But right now I just want to talk about the attractive forces. The next one is hydrogen bonding. I should have drawn this arrow a little bit longer. Actually a lot longer. Hydrogen bonding. That is a dipole-dipole attraction, but it's strong. A strong dipole-dipole. That's because it's between molecules that have a strong dipole, namely OH, NH, and HF. For instance, if I have a molecule, I'll put it here actually, NH3. Ammonia has strong, or has hydrogen bonding, which is a strong dipole-dipole attraction. because nitrogen is a fairly electronegative atom and it has a partial charge. And we'll designate partial charges with this delta plus electronegative. It draws electrons towards it, so it's actually partial negative, right? Electrons have a negative charge, partial negative, rendering the neighboring hydrogens partial positive because the nitrogen is drawing electrons towards it. Now, some of you may prefer, there are other ways to show partial charges. Some of you may prefer dipole arrows. So you draw the arrow towards the more electronegative atom, like that. Okay? So this can do hydrogen bonding with other molecules that can have an attraction to this partial positive H. Okay? Technically, the other molecule has to be bonded to that H via an O, N, or F as well. A very specific definition because these are especially strong. And the last set of IMF attractions are ion dipole forces. We see this with sodium chloride because you could separate the Na plus from the Cl minus. And let's draw water. Let's do it in green. How do I want to do this? Because oxygen is the electronegative atom, the O is attracted to the positive sodium. But in the chloride's case, H is partial positive and it's attracted to the negative. So it's truly ions, and then we have partial charges. I was about to say something else and now I forgot. Anyway, I forgot. Anyway, if we look at the strength, yes, ion dipole forces are typically the strongest, but if you have a very, very, very large molecule, then you have many, many London dispersion forces, and then a lot of London dispersion forces may actually be stronger than a single hydrogen bond. So the number of these attractions count as well in terms of the strength or in terms of how well the solvent surrounds the solute. Normally when we talk about this, we talk about boiling point, but not in this case. Now we're using these attractions to solvate solute molecules. The last topic, I want to talk about the energetics of dissolving. And I have a picture from the textbook, and we'll take notes on this picture here. Very good picture. This is definitely a picture is worth 1,000 words example. Hopefully you can see the detail. We are talking again about the energetics. Mostly in this video, the enthalpy. So the energetics of dissolving. Okay. Don't look at this picture just yet. But think again about our sugar and our tea, water. Okay, you have your water molecules, okay, blue molecules. And you have your tea, you have your sugar. And again, molecules. In this case, in the form of a solid. In this case, the form of a liquid. When you mix these two, you can measure the heat or the enthalpy, same difference, of, it's called solution. So it's the heat of solution, quotes, or literally delta H SOLN. Sometimes when you mix things in water, it gives off heat. Sometimes it actually absorbs heat, endothermic and exothermic. But how do we figure out delta H's solution? Well, we could break it up into parts. And the parts they are breaking it up into it's a little bit tricky, but let me show you what to focus on. You start out with, the sugar. and the tea. Okay, the tea water. Okay, and they're separated. And really, what we're doing when we take a spoonful of sugar and throw it in the tea, we're doing this arrow right here, because here's the solution, right? So we're going from here, messing up this drawing a lot, from here to here. Okay, I don't want to draw too much on this because it's such a good diagram. But Hess's law says, well, if you could break it up into parts and understand the enthalpy in each of those parts and add them up properly, we should get this dude right here. See, do you see how this is what we need? This delta H of solution. And don't forget, heat, Q, as we know it, and enthalpy are interchangeable when the pressure is constant. And for mixing, yeah, the pressure is constant. It's atmospheric pressure. So anyway, what are the two parts? Now let's focus on where my errors are. The first part is this one here. Breaking up the solute. See, the solvent is the same. So that we'll call delta H1, and this is separate. Is that how you spell separate? Separate solute molecules. Let me zoom out just a tad. Okay. Oh, by the way, this is from the textbook Atoms First by Burge and Overby. Anyway, we have that. The next step is this one right here. We separate the solvent. Why? To make space, right? To make space for the solute. So that is delta H2. Let's separate solvent. Okay, they're both up arrows. So yes, it requires heat. So this is endothermic, and we have an endothermic. Am I going off screen? I feel like I am. Okay. So this is positive, right? A positive delta H and a positive delta H. Look at this red arrow. That is now the interplay between the two separated solutes and solvent. So that's plus delta H, 3. But what is that? That is now the IMFs interacting. These are the attractive forces. Attractive forces between the solute and the solvent. And they're attractive. They release energy. So now we get exothermic, and it releases energy. Negative delta H. All of those equals, again, the heat of solution. Now, in this case, right, in this case, what is it? It is endothermic. See, the heat of solution is positive, endothermic. What does that mean? It absorbs heat, and the water gets cold. C-O-L-D. Why? Because the mixing is absorbing heat away from the water. Okay. Now, if this heat, the heat number 3, the IMF attractive forces, if it releases a lot of energy, then imagine that red arrow going way below, way down here, and then your addition of 1, 2, and 3 will end up having a red arrow going down from the starting place, right? That would be exothermic. If we had a final blue arrow going down, that would mean that delta H solution is less than 0, negative. And that happens because think of what is ice packs. Ice packs, you're mixing a solid with water, and it happens to be endothermic. It makes the environment cold. But the opposite is warming pads, right? Or hand warmers. We discussed this a couple of units ago, and that is exothermic. And there are solutions, things that you could find at home. Try dissolving a lot of salt in water and feel the glass. Is the glass going to be cold or hot? I'll let you discover that on your own. Now, I would be remiss in telling you that not only is there a heat component to mixing, but there's also an what's called entropy component. But we are not going to talk about the entropy component of mixing. The heat component will take care of a lot of the problems that we'll see in this unit. Entropy component, meaning that now we're looking at the water's order, the molecules, how they are ordered or disordered. So this is a measure of disorder. You've heard the phrase, the universe tends to go towards higher entropy. That means more disorder. It is important, but not in our cases. This is most important when dissolving. It's called hydrophobic molecules. Molecules that are very hard to dissolve in water. And we will save it. Save this discussion for when? When you're out of Gen Chem. So we're going to save this discussion for organic or orgo, and when we talk about drug molecules in organic chemistry. You have that to look forward to. All right. The videos again in this unit, we're going to talk more about solution. I think the next one is going to be about polar substances and how water can dissolve better polar substances rather than non-polar substances.